How do you produce millions of liters of drinking water in the Sahara, a place where rain can disappear for years? Normally, there are only three answers: drill deeper wells, pump water across enormous distances, or build an expensive desalination plant. But on a mountain at the western edge of the Sahara, engineers tried something that looked almost absurd. They built giant nets and placed them directly inside a cloud. By morning, microscopic droplets covered the mesh, merged, and ran into gutters. Across 31 collectors, one productive foggy day could yield roughly 37,000 liters, nearly 10,000 gallons. Repeated through a season, those droplets became millions. But the fog rode in on violent winds. Earlier nets had turned into sails and torn themselves apart. And after dust covered the surviving mesh, the first water entering the gutter could be too dirty to send into a home. Stay until that first dark stream leaves the net, because it reveals why catching water was only the beginning. The breakthrough was a system that survived the wind, rejected its first harvest, and delivered clean water without a pump. Subscribe and leave a like for more hidden engineering stories. The first warning came from the Atacama Desert in Chile. In the late 20th century, the fishing village of Chungongo depended heavily on water delivered by truck. Local sources were limited. Deliveries were expensive, and families waited for limited shipments in one of the driest regions on Earth. Yet, above the village, a coastal fog called the Camanchaca regularly crossed the ridge at El Tofo. Researchers stretched large plastic nets across its path. Wind pushed the fog through the mesh. Droplets struck the fibers, joined together, and fell into gutters. A pipeline carried the water downhill. The installation eventually grew to roughly 100 collectors and supplied around 15,000 liters on an average day. That is nearly 4,000 gallons of water. Gardens appeared, fruit trees began growing. A village that had waited for trucks was drinking from a cloud. Then the wind climbed past 60 miles per hour. The broad, flat nets became sails. Cables pulled tight, metal supports bent, seams ripped, gutters twisted away from the falling water. Some panels tore into strips, others bulged so far that the droplets missed the collection channel entirely. The surface could be covered in water while the reservoir below remained empty. Failure exposed the central contradiction of fog harvesting. Wind was not merely an enemy. It was also the delivery system. Without wind, the droplets would never cross the mesh. But when the densest fog arrived with powerful gusts, the machine could be destroyed by the same force that brought its water. The principle worked. The collector did not. Years later, German industrial designer Peter Trautwein examined damaged and poorly maintained fog collectors in other countries. He saw the same mistake repeated. Engineers were treating wind as a force to defeat with greater rigidity, but a mountain storm will usually win that contest. Trautwein began developing a different kind of collector. It would not stand motionless against every gust. It would remain anchored where strength mattered, flex where movement was unavoidable, and direct dangerous loads toward parts that could be replaced cheaply. That idea eventually became Cloudfisher. To test it, the project turned to Mount Bout Mesguida in southwest Morocco. The summit rises nearly 4,000 feet near the Atlantic and along the edge of the Sahara. Below it, villages could spend long, dry periods with declining wells and unreliable supplies. But high above them, a TV tower kept getting wet. Whenever fog swallowed the summit, droplets formed on the tower's exposed metal and ran down its legs. The villages below could remain dry while water appeared on ordinary steel above them. That observation changed the question. The region was not completely separated from water. The water was passing overhead in a form that no well could reach. To the west lies the Atlantic Ocean and the cold Canary Current. Moist ocean air cools over the coastal water, helping form low cloud. Wind carries that cloud inland until the mountain rises directly into its path. For roughly half the year, that summit repeatedly disappears inside fog. Production rises and falls with the season. On a typical foggy day, every 11 square feet of mesh may collect around 6 gallons of water. During the strongest months between November and February, the yield can climb much higher. This mountain does not receive water continuously. It has a harvest season. Fog is not visible water vapor. It is a cloud of tiny liquid droplets. They are large enough to wet a surface, yet often too small to collide, grow, and fall as rain. So the summit can remain inside a cloud for hours, while the villages below receive nothing. The mountain is wet. The village is thirsty. For local families, that difference was measured in footsteps. Women could leave before sunrise and walk more than 3 miles toward open wells, hoping to finish before the heat became unbearable. Girls were expected to help carry the load, even when that meant missing school. The isolated routes also left them exposed to dangers that a household tap would quietly remove. But the water crisis was not only emptying wells, it was emptying villages. As groundwater continued falling, families sold their homes and abandoned rural life. Nearly half the local population eventually moved toward the cities. Without a new source of water, the settlements below the mountain were not simply facing greater inconvenience. They were slowly disappearing, yet nature had already completed the most energy-intensive steps. Sunlight evaporated ocean water. The atmosphere transported it. Cooling formed the droplets. Wind delivered the cloud to the mountain. The missing piece was a surface capable of making the cloud fall. And the best clue was not another machine. It was a tree, Aun El Hierro in the Canary Islands. Stories tell of the Garowe, a sacred tree that supplied water where dependable rivers were absent. Moist trade winds drove cloud through its canopy. Droplets struck leaves and branches, merged, ran down the trunk, and entered basins below. To anyone who could not see the droplets inside the fog, the tree appeared to create water. It created nothing. It combed water from a moving cloud. The canopy also demonstrated why a solid wall would fail. Air diverts around a solid obstacle and carries much of its water with it. A porous three-dimensional surface allows the air to pass while giving droplets thousands of opportunities to strike something along the way. And the Garowe was not nature's only fog collector. Pine needles and redwood canopies strip moisture from passing cloud. Namib desert beetles guide droplets across textured bodies. Lizards in the Australian outback move condensed water through channels in their skin. Cloudfisher did not invent the principle. It enlarged it, standardized it, and connected it to a tap. If you were designing the new collector, would you make it stronger or let it move? Tell me your answer and where you are watching from. The solution used both ideas and one deliberately weak component that could save the entire machine. At first glance, a Cloudfisher unit looks almost disappointingly simple. A steel frame is anchored into the mountain. Inside it hangs a three-dimensional monofilament mesh. A plastic geogrid supports the collection surface. Rubber expanders connect it to the frame, and a flexible food-safe gutter waits below. But the real process begins at a scale the eye cannot follow. Imagine one droplet approaching a single fiber. The air curves around the strand, but the droplet has inertia. If its path carries it close enough, it strikes the material and remains there. Another droplet arrives, then another. They merge into a bead. Its weight increases until gravity pulls it down the fiber toward the gutter. In the end, collection efficiency comes down to three variables: how thin each fiber is, how wide the gaps are, and what the material does when a droplet strikes it. Make the fibers too thick or the gaps too open, and much of the fog passes through untouched. Make the mesh too dense, and air begins diverting around the collector. Wind load rises. Openings become blocked by water, and the net starts behaving like the sail engineers were trying to eliminate. Choose a surface that holds water too strongly, and the mesh looks wet but produces little usable flow. Keep growing drops exposed too long, and the wind tears them away and returns them to the cloud. The best collector is not the one that looks wettest, it is the one that gets captured water off its surface fastest. Then comes the part that allowed the system to survive. The geogrid limits how far the mesh can bulge. Flexible connections spread wind forces instead of concentrating them at a few rigid points. The gutter moves with the collection surface, so falling water can still reach it while the panel flexes. And in an extreme gust, a rubber expander can fail first. That is intentional. An expander is cheap, visible, and easy to replace. By becoming the controlled weak point, it can release a dangerous load before the expensive mesh or steel structure is destroyed. The weakest component protects the whole machine. With smaller, modular surfaces, ultraviolet-resistant materials, flexible attachments, and an anchored frame, Cloudfisher can survive winds approaching 75 miles per hour. Not because it refuses to move, because every movement and every possible failure has somewhere safe to go. It is the midpoint of the story. At first, the invention seemed to be a special net that pulled water from the air. The real invention was a system that controlled collision, drainage, wind, pressure, contamination, storage, and repair. Engineers could now make thousands of liters leave a cloud without the collector tearing itself apart. Then they discovered that the water was trapped on an isolated summit. Below the summit, 16 villages were scattered across steep, rocky terrain. A source at the top of a mountain is not yet a water supply. Until it reaches a home, it is only a more expensive form of fog. The pilot infrastructure required nearly 4 miles of pipe. As the project expanded, the network eventually stretched to roughly 15 miles. connecting collectors, treatment equipment, reservoirs, villages, and individual houses. This second machine looked far less impressive than the black nets on the ridge. It consisted mostly of pipe, valves, tanks, fittings, meters, and trenches. Yet without it, not one captured droplet would change life below. Local crews moved materials through rugged terrain where heavy construction equipment could not simply reach every slope. Pipes and tools still had to cross rock and heat. The futuristic collector depended on ordinary plastic pipe and exhausting human labor. But the mountain that made construction difficult also supplied the solution. The route descended thousands of feet. Once water entered the pipeline, gravity created enough pressure to move it toward the settlements. No continuously powered pump was needed to force every gallon downhill. The mountain became the pump. But a drop that steep creates dangerous pressure inside the pipe. The water could not simply be released into one uninterrupted line. Reservoirs and cisterns broke up the journey. Valves regulated the descent. Smaller pipes divided the supply. Storage separated the weather above from demand below. On foggy days, the collectors filled the system. On clear days, households used what had been stored. The net produced when the weather allowed. The reservoir delivered when people needed it. There was also a human network to build. Scarcity already had a price, a schedule, and people who depended on the old water economy. A new source changed who paid for water, who managed it, and who no longer had to organize every morning around a distant well or delivery truck. Residents also had to trust the idea of drinking a cloud. A black net might impress an engineer, but a household needed to know whether the water was safe and whether the system would continue after foreign specialists left. Darcy Hamad therefore made local management part of the infrastructure. Residents were trained to monitor supplies and report leaks. Household meters made distribution measurable. Mobile reporting and weather instruments allowed faults to be identified without waiting for an overseas specialist. Women played a central role because they had long carried and managed household water. Connecting a tap did not erase that knowledge. It changed what that knowledge could accomplish. For some women, the new supply returned more than 3 hours each day. Time once spent walking and carrying containers could move toward children, education, Argan cooperatives, or gardens beside the home. One resident looked across the dry ground and imagined what might come next. Tomorrow we'll have fog tomatoes. The most valuable thing moving through the pipe was not measured only in liters, it was measured in hours returned. And the price made the change even harder to believe. Residents paid roughly 40 cents for about 260 gallons of fog water delivered to their homes. The cloud itself was free. The small charge helped keep the ordinary parts of the miracle, the pipes, tanks, meters, inspections, and repairs, working after the engineers left. By now, the system seemed complete. The Atlantic supplied the moisture. The mountain intercepted the cloud. The mesh captured the droplets. Gravity moved the water. Reservoirs balanced foggy and clear days. Then the summit disappeared inside a wall of Saharan dust. Wind drove fine orange particles across the ridge. Dust coated the fibers, narrowed the openings, and settled into the gutter. A collector designed to intercept microscopic water droplets had become a giant filter for the desert itself. The immediate danger was not merely lower production. It was what would happen when the fog returned. The next cloud reached the mountain and the mesh began collecting again, but the first droplets struck a dirty surface. As they merged and ran downward, they carried dust, salt, organic material, and everything else that had accumulated during the dry period. The first stream, leaving the net, could run dark. If that water went directly into storage, the machine built to solve a health problem could create one. But if dust remained cemented across the mesh, the collectors would lose the open geometry that made them work. The system had to use its first harvest to clean itself and refuse that water before it entered a home. Early runoff was therefore kept out of the drinking supply while it rinsed the exposed surfaces. Filters removed suspended material, treatment protected the cleaner flow that followed. Earlier versions of the Moroccan system used sand and cartridge filtration, followed by ultraviolet treatment, with solar power supporting treatment and monitoring equipment. The collection surface needed no electricity. Safe water still required decisions. Desert plants face a similar sequence. Their spines, leaves, and textured surfaces collect moisture while remaining exposed to dust. Early droplets can loosen contamination before later water reaches the plant. Cloudfisher is not a mechanical cactus, but both survive by allowing the first moisture to clean the collecting surface. The storm revealed the final truth about the giant nets. Catching clean fog was easy, compared with managing a dirty machine after the fog disappeared. And even this supposedly futuristic idea carried a much older shadow. Long before polymer mesh and German wind tests, communities along the arid Pacific coast of South America learned to exploit water carried in coastal fog. In southern Peru and neighboring desert regions, ancient channels, basins, vegetation, and simple barriers were positioned where moist air crossed high ground. Leaves, reeds, stones, and terrain perform the work modern fibers now do faster and more predictably. Cloudfisher's materials are modern. Its basic idea is ancient. What changed was scale. A natural canopy or small barrier could sustain a limited settlement. Engineered modules could be measured, repaired, connected to treatment, and linked through miles of distribution pipe. On the mountain, 31 collectors provide more than 18,000 square feet of collection surface. In productive conditions, each 11-square-foot section can harvest more than 5 gallons in a day. Across the complete array, that can mean approximately 35 to 37,000 liters during a strong fog event, or close to 10,000 gallons. This is where the word millions must be understood. No single panel produces millions of liters overnight. The scale appears through repetition. More than 18,000 square feet of mesh perform the same microscopic collision at once. Every fog event adds another volume. Every season repeats the process. Even an earlier 6,500 square foot pilot was estimated to produce about 2.3 million liters in a year when weather patterns held. That is more than 600,000 gallons. The expanded project reached towards 16 villages and roughly 1,300 residents. The millions emerge one collision at a time, droplet after droplet, fiber after fiber, cloud after cloud. But passive did not mean free. The collection surface consumed no electricity. Yet every new village still required steel frames, miles of pipe, storage tanks, transport, training, monitoring, and replacement parts. Plans to expand into more settlements depended on grants and donors. Our Cloudfisher could survive winds of 75 miles per hour, and the next installation could still be stopped by something invisible. The disappearance of funding. In 2016, the Moroccan project received recognition through the United Nations Climate Initiative Momentum for Change. The award mattered because it marked a shift in how the idea was seen. Fog collection was no longer merely an experiment hanging on a remote ridge. It had become an example of climate adaptation built around local geography and community management, but recognition did not turn it into a universal water machine. Cloudfisher cannot be placed anywhere in the Sahara. Humidity alone is not enough. A useful site needs actual fog droplets, sustained wind, suitable elevation, storage, maintenance, and a collector facing the correct direction. Turn a panel away from the prevailing fog-bearing wind and its yield falls. Place the same system on a flat inland plain where no low cloud arrives, and it may collect almost nothing. Climate patterns add another uncertainty. Changes in wind direction, cloud height, or fog frequency can reduce production even when every component works perfectly. Engineers can improve the fibers and geometry, but they cannot control the weather. But no material can harvest a cloud that never arrives. That limitation does not make the project less remarkable. It makes the location part of the invention. Cloudfisher works because the Atlantic, the Sahara, and a mountain briefly meet in exactly the right place. Engineers did not force one machine onto every desert. They found a stream of water moving through a particular landscape and built an entire production line around its path. Now follow one final droplet through that line. It begins over the Atlantic Ocean. Sunlight evaporates seawater. Moist air moves toward Morocco. Cooling forms a low cloud. Wind drives that cloud inland until Mount Boutmesguida rises into it. The droplet approaches a monofilament. Air curves around the strand, but inertia carries the droplet into the surface. Another joins it. Then another. The growing bead begins to move. While the wind flexes the net, rubber expanders spread the load. The geogrid controls the bulge. The moving gutter catches the falling water. If dust has covered the surface, the earliest flow rinses it away and is kept from the drinking supply. Filtration and treatment protect the cleaner water that follows. A reservoir stores it. Then gravity takes over. The droplet descends through a network built across rock and heat. It passes tanks, valves, meters, and smaller distribution lines. Thousands of feet below the cloud, a household tap opens. What looked like water produced from nothing was actually a factory stretching from the ocean to a kitchen. The Atlantic supplied the raw material. The atmosphere transported it. The mountain lifted the collector into its path. The mesh converted movement into collision. Treatment protected the supply. Storage separated weather from demand. Gravity completed the delivery. Local residents kept the chain alive. So how do people produce millions of liters of drinking water in a place that appears to have none. They do not move the ocean into the desert. They intercept a small part of the ocean already moving above it. And while you were watching this story, fog may have been crossing that ridge. Droplets too small to fall as rain may have been striking black fibers, joining together, entering a gutter, and beginning the long descent toward a home. The Sahara was never entirely without water. It was missing a surface designed to catch what kept passing overhead. Subscribe and share this investigation if you want more stories about the hidden systems turning impossible environments into working machines.